The topic of this lecture is pre-measures and the Hahn-Kolmogorov extension theorem. So, let me briefly recall what we have done, and we will put this new topic, today's topic, in that context as well. So, recall that we have defined what are called abstract outer measures, and from abstract outer measures we have given a theorem which is the Kara-Theodori extension theorem, which once you have an abstract outer measure, the Kara-Theodori extension theorem via the notion of Kara-Theodori measurability, this gives you a measure, a sigma algebra, and a countably additive measure on that sigma algebra. So, let me write here abstract outer measure on mu star on x, and this gives you the Kara-Theodori extension theorem gives you a measure mu and a sigma algebra B on x, and here we have mu is equal to simply the restriction of the outer measure to this sigma algebra B. So, we denoted our B was C mu star of x, which was the collection of Kara-Theodori measurable subsets. This collection was Kara-Theodori measurable subsets of x. So, this was the prescription of the Kara-Theodori extension theorem. Once you have an outer measure, how to produce a sigma algebra and a measure which satisfies not only countable subadditivity but also countable additivity for disjoint sets in the sigma algebra. Okay, so here of course there is a parallel with what we have seen before. So, the abstract outer measures are exactly generalizations of the Lebesgue outer measure, and so the Kara-Theodori extension theorem gives you a measure. So, let me write it as m star, and the Kara-Theodori extension theorem, let me write it CET for short. It gives you a measure MC, C for Kara-Theodori, and a sigma algebra Cm star of Rd on Rd. So, now the question arises whether this measure MC is precisely our Lebesgue measure or not. Is MC equal to M, the Lebesgue measure, and Cm star Rd is equal to LRD. So, the answer to this question is in the affirmative, and this gives you another way to define the Lebesgue measure as the measure induced by the Kara-Theodori extension theorem. The Lebesgue measure is the measure induced by the Kara-Theodori extension theorem from the Lebesgue outer measure, and the sigma algebra that it gives is exactly the sigma algebra of Lebesgue measurable sets on Rd, and the measure is exactly the Lebesgue measure. So, we will answer this question here, but this specific instance of the Lebesgue measure is then a generalization for the sorry, so this measure mu that we get in the sigma algebra C mu star x on an arbitrary set x is then a generalization of the Lebesgue measure that we have already seen. On the other hand, remember that our Lebesgue outer measure came from something more basic, which was the elementary measure or the Jordan measure. So in fact, we defined the Lebesgue outer measure using only boxes, and so it was given by the elementary measure on the elementary subsets of RD. So the question arises whether you can take an abstract version of what is an elementary measure such that it will give you this abstract outer measure mu star on x. So this concept is precisely what is called a pre-measure on a Boolean algebra B0, and this passage from a pre-measure to an abstract outer measure is exactly this Hahn-Kolmogorov extension theorem. So this bottom row which goes from the elementary measure to the Lebesgue outer measure and then to the Lebesgue measure, provided we prove that we get exactly the Lebesgue measure using the Caret-Theodori measurability condition as well, then is generalized to this concept of a pre-measure on a Boolean algebra, which then gives you an abstract outer measure, which then gives you a measure on the sigma algebra of Caret-Theodori measurable subsets. And in fact, this measure mu star, this outer measure mu star given by the Hahn-Kolmogorov extension theorem also satisfies that the restriction of this outer measure on this Boolean algebra B0 from which we started is precisely this mu naught, which is the pre-measure. So let me write it here, mu naught, a pre-measure on a Boolean algebra B0, and this gives you an abstract outer measure which, when restricted to sets in B0, gives you mu naught, which is why it's called the extension theorem, because it's extending this pre-measure to an outer measure, and then a further extension theorem due to Caret-Theodori then gives you that a measure on a full sigma algebra B or C mu star x. So this is the layout of our conceptual layout of our plan, which is to either start from an abstract outer measure. If you are given an abstract outer measure, then you can use the Caret-Theodori extension theorem to go to a measure. But if you are already given a pre-measure, then you can get an outer measure and then a measure using the Hahn-Kolmogorov extension theorem. So we will also answer in this course that even if you don't have a pre-measure, you can get an outer measure given a very mild condition. So abstract outer measures are quite easy to achieve, and then we will also answer that for the specific case of the Euclidean space RD, whether the measure induced by Caret-Theodori extension theorem from the Lebesgue outer measure is precisely the Lebesgue measure or not. So this is our plan for today's lecture. So let me begin by defining what is a pre-measure. First, before defining what is a pre-measure, we define what is called a finitely additive measure on a Boolean algebra. B naught on a set X. So a finitely additive measure, on a Boolean algebra B naught on X is a function mu naught which takes elements of B naught, so subsets of X lying in the Boolean algebra, and gives you a non-negative extended real number, so it can lie between 0 and infinity with both endpoints included, and such that it satisfies two axioms. So the first one is the empty set axiom, which is that mu naught of the empty set should be 0, and the second one is the finite additivity axiom, the finite additivity axiom says that if E and F belong to B naught and they are disjoint, E intersection F is empty, then mu naught of E union F equals mu naught E plus mu naught F. So for example, if you take the elementary algebra ERD and define M from this elementary algebra ERD bar 2 0 plus infinity. So here I am using the notation M, so it shouldn't come as a surprise that it's going to be the elementary measure, which is defined as ME is equal to the elementary measure of E. Well, I should maybe change M to M bar here. M bar E is at the elementary measure of E if E is elementary, and equals plus infinity if E is co-elementary. So recall that the elementary algebra was the collection of elementary and co-elementary subsets of RD. So for elementary subsets we have the elementary measure, and for the co-elementary subsets we have the value plus infinity. So this is a finitely additive measure, as one can check. It's quite easy to check because we have already proved that it is finitely additive on elementary subsets, disjoint elementary subsets. But if one of them is co-elementary, then both sides are plus infinity and basically you are done. So this is a finitely additive measure. Similarly, if you take the Jordan algebra and you can similarly define an extended Jordan measure for Jordan and co-Jordan measurable subsets, and you will get again a finitely additive measure. So this is the prototypical example that we will be working with. So now a pre-measure is defined as follows. So if B naught is a Boolean algebra on X and mu naught is a pre-measure, is a finitely additive measure, then mu naught is called a pre-measure if it satisfies one further property. If given a collection n equal to 1 to infinity En of elements of B naught which is disjoint. So it's a disjoint collection of sets within B0, and the union n equal to 1 to infinity also lies in B0, then the mu naught of this union, countable union now, is equal to the sum n equal to 1 to infinity mu naught En. So of course, if you want to extend a pre-measure to a measure, then this should be a necessary condition. This countable additivity on the Boolean algebra itself should be a necessary conditions, meaning exactly this part that I wrote here, that if you have a disjoint collection such that the union also belongs to the Boolean algebra, then you should have the countable additivity property satisfied by a pre-measure, so that it can become a measure. So if you are expecting something to become a measure, then it should already satisfy this countable additivity property for unions which again lie in the Boolean algebra. So now we are ready to state the Hahn-Kolmogorov extension theorem, and this says that if mu naught is a pre-measure on X, so here B naught is a Boolean algebra on X, then there exists a sigma algebra B naught, B containing B naught, and measure mu on B naught, measure mu on B, which extends mu naught, which means that when you restrict mu to elements of B naught, you get mu naught, or in other words, if E is an element of B naught, then mu of E is equal to mu naught of E. So this is the extension part in the Hahn-Kolmogorov extension theorem, because we are extending a pre-measure to a measure on a full sigma algebra. So let's see the proof for this wonderful theorem. First note that if we define for any set E in X, mu star E to be, so this is a definition, we define it to be the infimum of these sums I equal to 1 to infinity m ei, such that E can be covered by this collection of sets I equal to 1 to infinity ei, and each ei belongs to our Boolean algebra B naught for each I. So as you can see, this is almost a replica for the definition of the Lebesgue outer measure. So here I should rather write mu naught, because we don't have the elementary measure but rather the pre-measure. So this my mistake says that, of course, we are just repeating the definition of the Lebesgue outer measure, which was defined using coverings of sets by countably many boxes, and then taking the infimum of these sums 1 to infinity of each elementary box. So here we are replacing the boxes by elements of our Boolean algebra B naught, which is given, and then we are doing exactly the same thing as before. So we can immediately check that mu star is in fact an outer measure. So this I leave you to do this as an exercise, and in fact we need not even have this pre-measure to define the outer measure. In fact, if you go to the proof of the definition of the Lebesgue outer measure and the proof that it satisfies all the axioms of the outer measure, then you will see that the following lemma is also quite easy to show, which is that if E is a subset of the subcollection of the power set of X, and such that phi and X both belong to this collection E, and rho is a map from E to the non-negative extended reals, such that the empty set gives you the value 0 when you apply rho to it. So this is the empty set axiom. So rho is any map, need not be finitely additive, but it is any map which satisfies the empty set axiom. Then mu star E defined as the infimum of the values rho E I equal to 1 to infinity, such that E is covered by this union I equal to 1 to infinity EI, and each EI belongs to E, is defines an outer measure on X. So this is exactly just repeating the same arguments for the proofs that we gave for the Lebesgue outer measure that was defined using the elementary measure, and you can basically repeat each argument here to show that this is an outer measure. So in fact, when we define it using a pre-measure, of course the pre-measure satisfies this empty set axiom, and the Boolean algebra satisfies these the property that an empty set and the whole set X belong to the Boolean algebra, and so we can define an outer measure using this prescription. So by the Kara-Theodori extension theorem, the Kara-Theodori extension theorem implies that mu star gives us a sigma algebra C mu star X and a measure mu, which is the restriction of mu star to this sigma algebra C mu star X. So once we have a pre-measure, we can define an outer measure, and from the outer measure we use the Kara-Theodori extension theorem to get a measure. So now we have to show that this measure that we get extends mu naught. So first we have to show that B naught, the Boolean algebra, is a subcollection of the sigma algebra C mu star X. So this is, so let me denote it by B, which will be the required sigma algebra, and for any E in B naught, mu B naught, mu E naught, is equal to mu naught E. So this means that mu when restricted to B naught is given by the exactly the pre-measure mu naught. So we have to show this. So remember that our sigma algebra was defined using the Carat-Theory measurability condition. So we have to show that if E is an element of B naught, then mu star, then for any subset A of X, mu star of A is equal to mu star A intersection E plus mu star A minus E. So this was the condition that was required to define the Carat-Theory measurability. So this will show that E belongs to the sigma algebra B, which was by definition this C mu star of X. So since mu star is an outer measure, we have that mu star A is less than or equal to mu star A intersection E plus mu star A minus E. This is by subadditivity. So this is finite subadditivity, but of course finite subadditivity is a consequence of countable subadditivity, and so we have this inequality. So it suffices to show that mu star A is greater than or equal to mu star A intersection E plus mu star A minus E. So let us use the fact that E belongs to this B naught. So we start with an epsilon greater than 0, and now we are going to use the definition of the outer measure. So suppose that further that mu star A is finite. Of course, if mu star A is plus infinity, this inequality holds trivially. So this is trivial if mu star A is equal to plus infinity. So we suppose that it is finite, and so there exists, this implies that there exists a collection En in B naught such that A is covered by the union of these Ens, and mu star, the sum n equal to 1 to infinity mu star En is less than or equal to mu star A plus epsilon. So this we can do by the definition of so this should be mu naught here, by definition of the outer measure that we have just defined. So now A intersection E is then covered by this union En intersection E, n equal to 1 to infinity, and since E belongs to B naught and Ens belong to B naught, so this collection is in B naught. So En intersection E belongs to B naught for each n greater than or equal to 1. This means that the outer measure of A intersection E is bounded above by this infinite sum of values mu naught intersection E. Similarly, we can show that mu star of A minus E is less than or equal to this sum n equal to 1 to infinity mu naught of En minus E. So therefore, if you add these two inequalities, we get mu star of A intersection E plus mu star of A minus E is bounded above by the sum n equal to 1 to infinity mu naught En intersection E plus mu naught En minus E, where we have collected the nth term in the series in the two series in a single term. So we have a single sum with the nth term given by the sum of the individual nth terms. But since E belongs to B naught, we have that mu naught En is equal to mu naught En intersection E plus mu naught En minus E, because this is a using the finite additivity property of the pre-measure mu naught. So remember that mu naught was a pre-measure, and to define a pre-measure we had assumed that it satisfies already a finite additivity property. So therefore this is less than or equal to the sum n equal to 1 to infinity mu naught En, and this is less than or equal to mu star A plus epsilon. This is because this is how we chose our Ens, so that the sum is bounded above by mu star A plus epsilon. So we are done, and we have shown that B naught belongs to B naught is a sub collection of B. Now we have to prove that for, so this is again to show that for E in B naught, mu E equals mu naught E. So that our measure mu that we got from the caret-theory extension theorem, when restricted to B naught, is given by mu naught. So mu extends mu naught. So this means in words that mu extends mu naught. So let's see how this can be shown. So if En n equal to 1 to infinity is a collection of elements in B naught such that E is covered by this collection, the union of this collection, then mu star of E is of course less than or equal to the sum of these mu naught En n equal to 1 to infinity. So in particular if you take the collection of the single set E, this is a collection in B naught, and the rest of the, if you want to take a countable collection, you can take the rest of the sets as empty. So then this implies that mu star of E is less than or equal to mu naught E, because by the empty set axiom all other terms are 0. So we have automatically this bound which says that mu star of E, which is mu of E, because E belongs to B naught, which we have shown that it belongs to the sigma algebra B, and we have this inequality. So it suffices to show that given any collection of these Ens in B naught such that E is covered by ENs given any such collection, we have mu naught E is less than or equal to this sum of mu naught ENs n equal to 1 to infinity, because then you can take the infimum on the right side and this would imply that mu naught E is less than or equal to mu E. So why is this true? Of course we have that E can be written then as a union En intersection E n equal to 1 to infinity, because En's cover E, and when you take the intersection it becomes an equality rather than an inclusion. So this implies by, and this belongs to B naught. So by the pre-measure axiom, we have that mu naught of E is equal to the sum n equal to 1 to infinity mu naught of En intersection E, and one can show that once you have a finitely additive measure, it is automatically monotone. I didn't specify it explicitly, but this is by monotonicity property. This is due to monotonicity of a finitely additive measure. So one can show that once map satisfies the empty set axiom and the finite additivity axiom, it also satisfies the monotonicity axiom. So by monotonicity we have that each individual term is bounded above by mu naught En, and so we are done. So this ends the proof. So we have shown that. Just one more thing to add here is that this equality here can be used because we can assume without loss of generality that is this collection En is disjoint. So in fact can write assume without loss of generality that En is disjoint, is a disjoint collection, for example by reducing it to the lacunae so that the union gives you the same union but with disjoint pieces, and then again you can use monotonicity.